Today we are going to study the remaining part from Units and Measurement, Maharashtra State Board Physics Textbook, Standard 11. Now let us study about dimensions and dimensional analysis, that is the uses of dimensional analysis, the application part of it. First of all, let us see what is meaning of dimensions. So for that, to understand it, before going to the discussion, before going to the definition part, let us try to understand it with the help of one example. So I'm taking here the simplest example of velocity. Velocity is displacement upon time Displacement is measured in terms of meter and time in terms of second. So, dimensions are expressed in terms of dimensions of if any of the fundamental physical quantity or any of the derived quantity, it has to be written. They always are expressed in terms of fundamental units. So here SI unit of velocity is expressed in terms of fundamental unit, meter and second. So to express dimensions, always it is referred as a square bracket. It is always written in terms of square bracket, where M for mass, L for length, T for time. Generally, many of the physical quantities they expressed in terms of mass, length and time. So here it is power, there is no mass term present here. So power of mass raised to 0. Power of mass is 0. Meter, the SI unit of length, it is, there is no power expressed here, so it is obviously 1. So it is L raised to 1. Second, it is no power is written and in the denominator, so it is -1. So dimensions of velocity are M, L and T. We will take one more example, well-known example of force. Force, we all know its formula. It is mass into acceleration. Mass is expressed in terms of kg. Acceleration is meter per second square. So here SI unit of force, it is Newton, but we need to express it in terms of fundamental quantities, so as to written in its dimensions, I mean the dimensions that can be written from it. So what is meaning? First of all, let me write the dimensions of it and then we will define the dimensions. So here mass term is there, it has T raised to, time term is written in the T raised to -2. Now let us see definition. The dimensions of any of the physical quantity are the powers to which the concerned fundamental units must be raised in order to obtain the unit of the given physical quantity. So to obtain unit of any of the physical quantity, we need to express it in terms of its fundamental physical quantity and the powers of it that determines the dimensions. So dimensions nothing but are the powers of that units of that physical quantity, where units are expressed in terms of its fundamental terms. Unit of that physical quantity is expressed in terms of fundamental units, and the powers of those units, that is, they are nothing but what the of the physical quantities we will take into consideration, and we will find its dimensions from its unit. Even if we don't know its unit, we can derive that unit also if we know its formula. Let us take volume density. Density is nothing but what? It is mass upon volume. Mass is expressed in terms of kg, volume, meter cube. So dimensions are written in terms of m1, L raised to minus 3. Here time term is absent, so it is t raised to 0. Or even if you don't mention this t raised to 0, this can also be written as m1 L raised to minus 3. That is also okay. Now we will find the dimensions of acceleration. Acceleration is meter per second square. Its formula is v minus u upon t minus 0, or it can also be written as dv by dt. So it is meter per second square. Therefore mass term is absent, so it is m raised to 0, L raised to 1. Time is in the denominator, so shifting it to the numerator, it will be t raised to minus 2, and it has to be written in terms of square bracket. Then linear momentum. Symbol is P, which is mass. Linear momentum, it is mass into velocity. Therefore it can be written as m into v. So kg, velocity is 1, here it is 1, here it is 1, and it can be in more simplified form, it can be written as s raised to minus 1, shifting this s to the numerator. So the dimensions are m1 L1 t raised to minus 1. Angular momentum. It is I into omega, where I is moment of inertia. Its SI unit is kg meter square. This is expressed, omega is expressed radians per second, but radian itself is a number, so it is only written as a per second. So it can be written as therefore dimensions of angular momentum are m1 L raised to plus 2 t raised to minus 1, that is m1 L2 t raised to minus 1. They are the dimensions of angular momentum. Now kinetic energy. Kinetic energy is half of m into v square. Its SI unit is joules. So 1 joule is equivalent with, in terms of fundamental physical quantities, we need to express, here it is kg meter square per second square. So the dimensions are, or it can also be written as kg meter square second raised to minus 2. Therefore the dimensions are m1 L2 t raised to minus 2. These are the dimensions of kinetic energy. Now next we will study about it. Impulse. Impulse is force into time, that is Newton into second. Newton is kg meter per second square, mass into acceleration into second. So this will get cancelled with this. So it will be kg meter per second. Many times question based on this units and dimension it must be asked. The dimensions of so and so physical quantity are same. So it has dimensions similar to linear momentum impulse. So let me express the dimensions m1 L1 t raised to minus 1. So these are the momentum. Already we have done with the momentum. We'll take some more examples. Torque. Let us take torque. Torque is force into displacement. Therefore, it is Newton into meter. That is kg meter per second square into this meter. That is kg meter square per second square. Therefore, dimensions are m1 L2 t raised to minus 2. Magnetic induction, let us say magnetic induction notation is B. There is a relation of B and the force, magnetic force F is equals to BI L, where this B is the induction, this I is current, and length, and here it is force. Therefore, to find the dimensions of magnetic induction B, we need to express this formula in terms of B, that is B is equals to F upon I into L. So it is Newton per ampere into meter. Newton has to be expressed in terms of its SI unit, that is kg meter per second square into this ampere into meter. Therefore, it will be kg second raised to 2 ampere. Therefore, the dimensions of magnetic induction are kg for mass, so it will be m raised to 1, s raised to 2, that is time raised to 2 in the denominator, so it has to be t raised to minus 2, ampere is in the denominator, so it is current raised to minus 1. Now let's study about the uses of dimensional analysis. Uses of dimensional analysis. This is very important use of dimensional analysis. First, that is to check the correctness of physical equation. So to understand this, let us take an example of in the examination, if you are not sure about the formula which you are going to use for numerical solving, So this is the best way to check the correctness of that physical equation. There's only one drawback, that is you cannot find the constant number included in that formula by using dimensional analysis. So frequency, check the correctness of equation. N is equals to 1 upon L square root of T by M. So in this given physical equation, N is frequency. It has dimensions T raised to minus 1, tension is the force, so has the dimensions of force m1 l1 t raised to minus 2, m, that is linear density, mass per unit length, so it is m1 l raised to minus 1. Now let us prove whether the dimensions of LHS equals to dimensions of RHS. These are the dimensions of LHS. Let me number it as equation 1. Dimensions of RHS. Which is 1 upon small l root of T by M. So let us write the dimensions. 1 upon L raised to 1 tension M1 L1 T raised to minus 2 divided by linear density M1 L raised to minus 1. Let us simplify it. Here this M1 cancels with this M1. L raised to minus 1 shift to the numerator. It becomes L raised to plus 2. Therefore, that comes out to be dimensions of LHS become this L raised to 1 shifting to the numerator, it will be L raised to minus 1. Here it is square root, inside the square root it is L raised to 2 T raised to minus 2. Taking it out of square root, this will become dimensions of LHS RHS will become L raised to minus 1 square root. Taking it out, or we will simplify, I will write one more step for it, that is L1 T raised to minus 1 raised to 2 bracket raised to 2. So this square root cancels with this 2. Therefore, dimensions of RHS becomes L raised to minus 1, L raised to 1, T raised to minus 1. This L raised to minus 1 and plus 1 will cancel. So what will remain is T raised to minus 1. This is equation number 2. So from 1 and 2 we can say that dimensions of LHS equals to dimensions of RHS. Therefore, given physical equation n is equals to 1 by L square root of T by M is dimensionally correct. Second use of dimensional analysis, it is to establish the relationship between related physical quantities. That is, we can derive okay. So let us consider that time period of, it is given that example, it is given that the time period of simple pendulum, it is dependent on length of the string and is also dependent on acceleration due to gravity. Then find the equation of time period of simple pendulum. Therefore, T directly proportional to L raised to A, we don't know power of it, and acceleration due to gravity G raised to B. This dependence is given. So, we are asked to find what is T. Let us derive it. Therefore, let me number this as equation 1. Where K is constant. Let us write the dimensions of LHS, RHS and then substitute it in the equation of equation 1. So the dimensions of T are we are given these dimensions. We know that we wrote these dimensions, so let us substitute it in equation 1. So on substituting in the equation 1, it will be T raised to 1 equals to constant. We cannot do anything with this constant. Let us simplify it. It must be B. Multiply with the power. More simplification gives us base same, power difference will be added. On comparing power of TL on both the sides, we get first we will compare power of P. So B we calculated, therefore A is equals to half. Now let us substitute we can write L raised to A, that is half, and G raised to minus half. It can be written as T is equals to K L raised to half G raised to half. Therefore, time period of simple pendulum that can be written as K into L by G. This is the time period of simple pendulum. Let us take one more example of it, that is, suppose we are given the dependence of pressure of the liquid column is dependent on height of the liquid column, density of the liquid column, and acceleration due to gravity of the position. So we are asked to find P. That is, we are asked to derive the formula of pressure P. Therefore, to find this pressure P, we need to first of all express this equation in terms of equality. Therefore, it will be P is equals to K H raised to A rho raised to B G raised to C. So, this is what our equation 1, where K is constant. Now let us write the dimensions separately for these four different physical quantities. Pressure P, force per unit area. So it is L raised to minus 1, T raised to minus 2. H, height, it has a dimensions of length, so L1. G, the acceleration due to gravity. Small g, that is meter per second square. L1 t raised to minus 2. And density rho, it is volume density, so meter per kg per meter cube. So it is m1 L raised to minus 3. Now putting all these values, putting all these dimensions in equation 1, we get let us substitute. On simplifying, we get simplifying L raised to, look here, L, L and L. L raised to A minus 3B plus C. Now look at M term, it is M raised to B, and T term minus 2C. Here is M1 L raised to minus 1 T raised to minus 2. On comparing powers of L, M and T, we get power of M. These are the M terms, so power of M, LHS 1, RHS B. Therefore, it gives us B is equals to 1. Second, power of L on both the sides. So looking here and here, this will be minus 1 is equals to A minus 3B plus C. And third, power of t. Power of t. Therefore, minus 2 is equals to minus 2c. Therefore, 1 is equals to, this 2 get cancelled from both the sides. Negative sign will also be absorbed. 1 is equals to c. Now, put b is equals to 1, c equals to 1 in 1. I'll number it as 2. In 2, we get minus 1, a minus 3 plus 1. Therefore, minus 1 is equals to a minus 2. Therefore, minus 1 is this 2 shifting towards the LHS. Minus 1 plus 2 is equals to a. Therefore, a is equals to 1. Put a equals to 1, b equals to 1 and c equals to 1 in 1. So what we get? P is equals to K H rho G. So this is what the equation of pressure that can be derived from dimensional analysis. We'll discuss few more example and one remaining application of dimensional analysis in our next lecture. Thank you.